So if we want to multiply together two matrices, A and B, the first thing you have to do is to make sure that their dimensions match in a particular way. So the number of columns in A has to be the same as the number of rows in B. Otherwise, the product isn't even defined. But if that's true, then we can multiply A times B. The result is going to be an M by P matrix, and the ij entry of that matrix will be given by this sum. We're using a summation notation here. It represents the sum over all possible values of k from 1 to n. And it's just a lot faster to write than to try to write out the product this kind of way. Now that term, that sum that we have here, is actually what we call an inner product of vectors, or you might know it as the dot product from vector calculus. You just take the corresponding numbers from the vectors, multiply them together, and add up all the results. So the ij entry of the product is the inner product of row I of A with column J of B. So here it is with numbers. If I want to find the product of these two matrices, A is 2 by 3, B is 3 by 3, so the product is defined. Sorry about that. The product is defined, and the answer is going to be 2 by 3 as well. And to get the answer in the first row, first column, I take the first row, first column, and take their dot product. So that's 6 plus 0 minus 2 is 4. If I want to find the 2, 3 entry, I take second row, third column. The inner product is negative 1 plus 0 plus 4, so that's 3. And in the same way, we can go ahead and fill in all the other entries of that product. Now, a vector is a special kind of matrix where one of the two dimensions has a length of 1. And if you just follow the same definition, we can identify two different ways to multiply vectors together. So one of those is the inner product, which we just talked about a second ago. So if I have a 1 by 3 vector times a 3 by 1 vector, the 3's match, the answer is 1 by 1. Okay, the answer is just a number. And so in this case it's 4 minus 4 plus 2, so the answer is just 2. A 1 by 1 value, or a number, we give it a special name in linear algebra. We call it a scalar. And because of that, we sometimes call the inner product a scalar product. But if we take those two vectors and put them in the opposite order, now the first one is 3 by 1 and the second one is 1 by 3. But that's okay, the ones match, and so the answer has to be 3 by 3. And again, if you think in terms of the first row and the first column, well, that's just a product of two numbers. First row, second column is 4, first row, third column is 4, and so on. You're actually just taking all possible pairwise products from the two vectors. And that's what we call an outer product. Now this is a good time to remind you of an extremely important fact in linear algebra, that the order of the multiplication counts. It's not commutative. In other words, A times B is not the same thing as B times A in general. Okay, and that's exactly what we have here. We have an AB and then we do BA. They're not even the same size. But even if they were the same size, they wouldn't be guaranteed to be the same. So you've always got to keep the order straight when you're multiplying matrices together, including matrices and vectors. Okay, another fact about the inner product is that you can't do it between every pair of vectors. So here I have a vector which is 1 by 3 again, but now the second one is 2 by 1, Well, 3 does not equal 2, and so therefore this product is undefined. However, you can always take the outer product. So the outer product here is 2 by 1 and 1 by 3. And so in fact that is well defined, and the answer is 2 by 3. And again, we just take all the possible pairwise products between the two vectors. A very important matrix to know about in matrix multiplication is the identity matrix. So it's a matrix, it's always an n by n matrix. And it's 0 everywhere except along what we call the main diagonal of the matrix, where the entries are all equal to 1. It's customary when there are lots of zeros in a matrix to not write where the zeros are. Anything that's missing is assumed to be 0. It's also customary to write the identity matrix in terms of its columns. So we use the lowercase e for that. So the columns are vectors e1 through en. E2, for example, has a 1 in the second position only. And these e's are sometimes called standard basis vectors. We'll be seeing them quite a bit. Now, it's a consequence of the rules of matrix multiplication that if you take A times EJ, what you get back is the jth column of A. And if you take the transpose of one of those columns, so that it's 1 by n, and take that times an n by n A, then the result is the jth row of A. And you can check that quickly. And furthermore, because of the way the identity is defined and the way matrix multiplication works, A times I and I times A is always equal to A. And that's even true if A is rectangular, as long as I has the proper size, whether it's on the right or the left. Finally, I just want to mention how these things are done in MATLAB. So a matrix product, AB, is done just as A star B in MATLAB. If the sizes of A and B are compatible, you'll get A times B in the matrix sense. If not, you get an error. There's also the idea of raising a matrix to a power. Okay, that only works for square matrices mathematically, and so that's the only way it's defined in MATLAB. So A cubed, for example, means A times A times A, although it might be computed quite a bit faster than that. If you have multiple multiplications in a product, A times B times C, well, they all have the same precedence, and so that's the same as A times B times C. Of course, matrix multiplication is associative, so grouping doesn't matter. And in fact, this would get you the same mathematical result, although I have to point out that depending on the sizes of these matrices, one might be a lot faster than the other. And so sometimes you have to be careful about writing those kinds of products. The identity matrix in MATLAB is returned by a function called I. So I of 4 would be the 4 by 4 identity matrix. And then finally, I want to alert you to one other kind of multiplication that's available in MATLAB. It's the element-wise operation. So you use a dot star for multiplication or a dot caret for exponentiation. And what that means is to do things element by element. So it's easiest just to see this by an example. It's a very simple kind of product where you just multiply the things that are in the corresponding positions. And for exponentiation, it's also defined the same way. You exponentiate each element of the matrix by the number. That's not the same thing as taking the matrix power. You have to be very careful with these operators too. Sometimes they're exactly what you want, but sometimes if you use the wrong one, you'll get a code which executes but gives you completely the wrong answer.